Hello on April 11th. Let's do it. Find the count of good integers. You are given two possible integers, n and k. An integer x is called k palindromic if x is palindrome and x divisible by k. An integer is called good if its digits can be rearranged to form a k palindromic integer. For example, for k equal to 2, 2020 can be rearranged to form a k palindromic integer, whereas 1010 cannot be rearranged to form a k palindromic integer. So I can start from a palindromic integer. Return the count of good integers containing n digits. Any integer must not have leading zeros, neither before nor after rearrangement. For example, 1010 cannot be rearranged to form 101. Okay, so basically nothing can be we start with some, so like we cannot end at 0, right? Because if you end at 0, you have to start with 0. Okay, so in our case, n equal to 3, so it has to be 3 digits, has to be divisible by 5, right? So we kind of know how many there are. So n equal to 10, so most is 10. So we can do, basically it doesn't matter because essentially it's just asking for permutations. Right? It's just like permutations. You find one and you can permute. But permute, we have to avoid duplicates. Huh. How do we avoid duplicates? And remember, it's palindrome, so half the digits are the same. I think I'll figure it out, maybe. But how do we find all the palindrome first? Divisible. I mean, k is 1 to 9. Divisible by 1 basically is all the palindrome. Right? By 2 it has to be this. By 3 we have its own rule. I feel like we can just find all the palindromes. Like if it starts with 1, well, we'll have some rules. Right? So like if it's 2, it has to be even. If it's a 3, let's say if it's 3, well, it does cover everything. So the special ones is just so So 3 is not special, 1 is not special, 2 is special, right? 3 is not. 4. Yeah, 4 doesn't have that much. So 1 is all. 2 is, 2, 4, 8. 2, 6, 8. That's it. Right, 2, 4, 6, 8. 3 is all. Right? 5 essentially is just 5. 6. Well, 6 is going to be. Yep, that's 6. 7, I think, is everything. Yeah, 7 is all. Nine. Yeah, 9 is everything. We can use this to our advantage. So 5, right? So we know the last one has to be 5. So basically we set last has to be 5. When last has to be, so you only have to go through half, right? And then we basically have done. Okay, so this is a settled. And then we, in the middle, we have a bunch of numbers. Again, you set half of it, and that half can be anything. So in this case, in the middle, we have 0 all the way to 9. Right, they all can be divided. Then we need to find out how many different numbers are there. So they will have like 10, so, right? Of course, for 0, we have to rearrange, right? So basically, for each one of them, right? For each one of them, each palindrome is different, so we consider each palindrome separately. And usually, I think, unless the palindrome has duplication themselves, it might as well be. But anyway, what we have is in the first position, right? We have basically how many choices? We have 2 choices, right? 505 is just 1 because this is the only position. Oh no, it's now 1. 505, right? So we have 2, 5, and 1, 0. So at the first position, we basically have only 1 choice, right? Second position, depending on which choice it is. Well, I choose 5. Now we have 0 and 5 for second position. So second position, we have 2 choices. And third position, we have 1 choice. So that's 2. Basically, 505. 550, 550, that's it. or the other one, 5 something 5. Again, the first have two choices. Right? Well, first has two choices. And the second position, oh, this is like the full analysis. Yeah, essentially this says we have to first find out the palindrome, and then for each one of them we have to check if it's divisible. And if it's divisible, we need to find how many. Oh, because the palindrome itself can be palindrome itself can be. Yep, yep. I can see. We can use the same, and then we just swap it. Oh, then you have duplicates. Oh my god. The duplicates is really getting into it. We can handle this by counter it, right? Because counter provides a unique signature of each palindrome. Unique signature of each palindrome. So okay, so now basically the core problem boils it down to I have a counter which contains all the digits that's being used. So we need to find out how many different ways we can make it. Right? We're not gonna make it. So how many different ways we can make it? And to do that we can say we start from something. Then we have a state. Then we say how many we can make it with this. And how many we can make it. But doesn't feel right. I mean, we can do full permutation, but how do we deal with duplicates? Right, we can say, yeah, we put 5 at the front. Right, we put 5 at front, then we have 2, and then they have 2 different ways. And that's it, so it will be 2. So each one will be 2. Right, so we'll put this number, then I have 2 different numbers, and then we'll do a permutation, which is 2. Right, that's 1. Or we can put the other number at the front. Right now we have 3. Right now we have 3. So from 1 to 9, we all have 3, so that's 27. But I have 505. Oh, 555 only 1. So it's 27 total. Oh, this is gonna be tough. I think the real test is this one. One, two, three, 4, 5, right? And then k equal to 6. That is the real test. So apparently 6, I have all these options, so I can say, okay, I put 6 at here, and then 6 must be here, right? Then we just find all the palindrome, all the 3 palindromes, all the 3-digit palindromes. Yes, it's actually that's it. We find all the 3-digit palindromes. So we need to find an n-digit palindrome. Starting from something, right? So you're always starting from something, right? N-digit palindrome, you start from something. So we start from 6, right? And then we have this, and we need to find all the start from 1, start from 0 palindrome, start from 1 palindrome, start from 2 palindrome. So all of this we need to find, right? Like start from 0 palindrome, and then we have to say 1, 2, 3, 4, 5, right? And then we start from 1 palindrome, start from 2, 3, 4, 5. But how do we know that they're divisible? Oh, the inside has to be divisible as well. Well, technically not true. It's just this because it's 6, right? But we can do 2. If it's 2, that's just 2 something plus something plus, yeah, it's not right. But there can be a lot of palindrome, right? Well, actually not that much. So yeah, so we start from 0. Okay. And give me all the palindrome. So we'll find 0 and 0, so we have this, give me all the palindrome. So that gives you 0. So we have 6, 0, 0, 6. And then we try to find, that's, if it works, then we push it in. Doesn't work, then it doesn't work. And then we go 1, right? And then, yeah, we go 2, we go 3, we go 4, we go 5. So we go for everything. Right, we go for everything. And remember, we can do 10. So if n is 10, and also k can be 1, which means all the palindrome. the amount of computation is quite high the way I'm thinking about. Because, you know, imagine it's 10 digits and then k equal to 1. Right? You start from 1, then you find everything, all the padding room in with this much. Right? And then all the padding room with this much. So yeah, you'll keep finding. And those are just palindromes. And for each palindrome, you have to save it somewhere. Then you have to see how many different permutations they have. Yes, it is palindromes, it is equal, but still. You set 1 down, and then you're gonna go in, and you can say, I'll set this number. Set this number, set this number, set this. So you can go outside in. Doesn't work. Okay, come out, change. Maybe really, you think about recursion. Well, technically, yeah. I mean, recursion, you go in only. It's not gonna be the end of the world, I think, recursion wise. Yeah, recursion. So we starting number, right? It's current digit, and how many digits? The length of the length. Yeah, the length. And then once you're done, you return it until we go to the top level. Then you have every one of them. When you get to the bottom, you can actually do. So I can just keep going until I hit the end. Then I can push it into a set if it's divisible. Right? Or do it in such a way that we know. Yeah, it could be just an array, which is totally fine. Right? Which is an array, and then we have the index. I have the index. And coming here, index, I can just choose to go from here, go from here, go from here, go from here, and that was good. Yep, so once we go down the recursion, so recursion towards the end, we'll get a number out, We'll check if it's divisible. If it is, then we put it into this set. Right, we go through all of them, then we get a set of all palindromes that's divisible. Okay. Now the question is, and all the palindromes are unique, right? They're unique palindromes. Then we need to see how many different versions can we permutate ourselves into, right? How many different versions? So we can say, at the first position, so we have a palindrome, right? So everybody counts as 2. Well, actually, everybody counts as, we have one count as the other. Well, that's fine. And basically, we cannot just permutate, because permutate we lose the state. We won't be able to know who's whom. So we'll get first number. We know the probability, how many different ways the first one can be. So we do that. For the second one, it depends. Right, it depends. Because the second one, if the first one we use this, then the second one will be different. Keep using it. I don't think that's the right way. Don't have a good argument. I don't have a good argument. I think I can find all the palindromes, but from palindrome to unscramble them into numbers. Yeah, I don't think, maybe you can have a different way. So we have the counter, right? Like 1 occurs 4 times, 2 occurs 3 times, like that, right? So from there, we need to produce an n-digit number. How can we do that? Or can we, if we really permutate, okay, can we identify which ones gets twice? Or is it even, so if we permute, okay, if we permute like 515, right? If we really truly permute, it's 3, so it should be 6 different ways, right? So we should have 515, 551, and then 155, 155, right? Because we can permute, and then 551 and 515. That's 6 different ways. And eventually, like this one gets repeated twice, this one gets repeated twice, and this one gets repeated twice. Huh. I wonder if repeating twice, because when you permute, right, when you permute, you get different permutations, and you get different permutations, and once you get different permutations, you have some numbers are the same, right? Because permutations doesn't really care. So you have permutations, right? And whenever that one it's related, so because it always gets, because the permuted version of that, right? The permuted version of that. So if you have one number repeated, you can permute and you can divide by 2. Because half the permutes will be exactly the same. Okay, now here is an interesting question that we need to solve this, I think. 2, 1, 1, 2. How do we write that? Well, I think we can start by writing it this way. 2, 1, 2, 1, that's it. And then 2, 2, 1, 1. Right, and then we have 2, 2, 1, 1 again. Right, because hold on, like we have 2, 1, 2, 1, 2 as 2, and 2, 1 set. So we have 1, 2, and 2, 1. That's it, done. Now we move 2 here, so we 1, 1. We have 2, 1, 1, right? And then we move. That's one of the ones, and we have another one, so we can do whole thing again, right? Because this position we have 3, right? Okay, that's done. And then we have the entire thing copy again. Right, I'll have the entire thing copy again because this 2 can be at the front. Now we have 1 in the front. 1, 1, 2, 2. 1, 1, 2, 2. Right? 1, 2, 1, 2. 1, 2, 2, 1. And we'll have another 2, 1, 2, 2, 1, 2, 2, 1. And the whole thing copy again. That's 24. Okay, that's the entire permutation. So apparently, because we have this duplicate, so whenever you have a 2, so the other one is complete duplicate, right? So you don't consider that. And then you have this 1, so the other one you also don't consider that. So immediately 24 divided by 2 is 12. But then within this 12, so this is kind of the, you can call it the top layer, right? The ones that, because everything is except for the odd number, right? Oh, except for the odd number. My lord. Okay, the odd number we have to handle it pretty much separately, but even numbers, right? Even numbers, then every number, right? Because the palindrome has its counterpart, so we basically only take half. So we permute everything and we divide it by half. But in this case, we have further, right? Because once we settle on 1, because we also have, you know, because these start with 2, these start with 1, so like yeah, we got it. And then once we remove that, right, so basically removing one number, and we have the remaining. And the remaining is still a palindrome, right? It's still a palindrome. It's a odd number palindrome. So we need to find out. So odd number palindrome, again, we can do all the permutations for odd number palindrome, right? So it's 3, so it's 6, right? So odd number palindrome. So basically, we don't think about this, right? We only look at this part. This is odd number palindrome. Now, odd number palindrome, we have the odd number, right? We can take it out, right? Odd number, we can take it out, and then we have all the remainder is even number palindrome. So that even number palindrome can do whatever they need to do to form all the unique ones, and then the odd one can just start to add. We can add at the front. We can add here. That's one. We got here, 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 here. We can add at every position, right? So essentially, we're saying if like we have two numbers, right? We have one. Let's say we have 1, 2. We have 2, 1. Right now we got the 3 put it in. So for this arrangement, we can do 3, 1, 2, 1, 3, 2, and then 1, 2, 3. For this, we have 3, 2, 1, 2, 3, 1, and 2, 1, 3. So that gives you 6, because this one can go to all the spots, right? It goes through all the spots. So now you have a even number palindrome. Now let's assume we get all different ways, right? All different ways, so they're all unique. And then for each unique, this can go through everything. So now, yeah, we take 2 out, so we have 1 and 1. Right? So when you get to only 2, there's only one way, it's just 1 and 1, right? And then you can start put 2 into it. So this one can become, 2, 1, 1, 1, 2, 1, and 1, 1, 2. So we have 3. So basically here we have 3 uniques. So that's 3, right? And then the next one, you have to analyze the same way. I don't think it will be that. Yeah, essentially it's 2 permute, right? It's 2, and then divided by 2, so you can only have half. So that's why it's only 1, and then it becomes 3, right? It becomes 3. So essentially in this case, we have even number palindrome. We do the permutation, and then divide by 2. Right? That's respective to all the ones that can start from the front, right? And we can even list them out, right? We can list them out, right? And for each one of them, I have it can go in for the remaining, so they can keep going, right? Keep going. Now, there's one thing that's good is because the palindrome doesn't really care about the exact number, it's the pattern, right? You can just find a count for a specific pattern, and we have to deal with the 0. Like 0 has to be dealt differently. Okay, so this one is good. Basically, we permutate, divide by 2, so we eliminate one layer of duplicate, right? Then for every one, we keep going on. Now, so the inside is odd number palindrome, right? So we get out, then we have an even palindrome again. So we do it again, right? We do it again, and then we apply the odd onto it, and then we get something, and then we get something. Okay, so my question is basic 2 parts. One is, how do you deal with 0? Now I think 0 should be dealt differently, right? Apparently 0 should be dealt differently. Yeah, I think the top level we probably need to loop it, right? The top level we probably need to loop it, just to make sure that we don't have to deal with this 0 situation. Okay, so internally, yeah, we don't worry. Okay, now is the second question. What do we have? What if we have something like this? 2, 2, 2. Well, 2 to 2 is only 1. That's actually not a good example. How about we say 2, 2, 2, 2, 4, 4, like this. Right? We have some repeats. More than one repeat. We can, do the same thing. We will permutate it, right? And then divide by 2. So in permutated divide by 2, essentially you're saying, okay, I basically, I don't know. So because we can say this 2 at the front, we have a bunch. This 2 at the front, we have a bunch. Right? This 2 at the front, we have a bunch. This 2 we have, and then we just 4 as a bunch. This 4 as a bunch. Right? So basically, this is what is if we permute everything. And in this case, all of these are exactly the same. Or these 2 are exactly the same. So, that's the tough part. It seems to me, right? It seems to me that what needs to be happen is you find all the digits, all the unique digits, right? And then you say we can only lead by these unique digits. So you eliminate all this and you eliminate all this because we only have 2 and 4. So we say, okay, now the first digit has to be 2. Right? The first digit has to be 2. Now we deal with the rest. Okay, yeah, we deal with the rest. So the rest will have whatever it has. And it's an odd number. Right. Well, since it's the odd number, what we're gonna do is that we find the one that is odd. We can do that. So we find the one that's odd and we take it out. Okay, we take it out. And then among the remaining, it's an even palindrome, right? It's an even palindrome. So for even palindrome, again, we'll go through them one by one, right? We'll go through them one by one. So, okay, so let's try to work this. And I don't believe we can find an easy answer. So we have 2, 2, 4, 4, 2, 2, right? So I say unique value is 2 and 4. When I do this, 2 has 4 count, 4 has 2 count, right? And now we say first is 2, right? Basically, that's what we do. First 2, we want to find how many is in total, right? And then if first is 2, then the next state will be 2 will have 3 times and 4 has 2 times. So that is the next level, right? So we can say that we'll do. So you can either do 2 or you can do 4, because none of them have been done before. So say, okay, I'll do 2, right? But again, I don't really think that's how you want to do it, because we'll find out that 2 is the odd one out, right? So 2 is the odd one out, and then without 2, what you have is this, right? So when you have this, we can say, okay, we have 4 digits, and they're palindrome in this shape. And you say, okay, maybe we can do, permutation it. Right, so we got a permutation, and then each one, I think, like 2 occurs 2 times, 4 occurs 2 times, 2 occurs 2 times, right? 4 occurs 2 times. So if I do palindrome on this, I'll divide by 2. So that's the total count. There shouldn't be any. So is there a generic pattern here? Oh, and also be careful, because here I have 4, right? And then 4 permutation is 24, and divided by 2 is 12. So we're saying we're 12 ways to arrange 2 and 4. Really? Well, I mean, again, we can say we take 2 out, and then this one we say we can take 2 out. Then basically 2, we have 1, 2, and we have 2, 4. So this is a 3 pattern. Right? And then this point we say we'll take 4 out. Now we have 1 and 1. This is a full permutation because it's unique. Right? It's unique. So this will give you 2. Right? This will give you 2 options. So basically we're saying that if we start with 4, I'll give you 2 options. So yeah, so start with 4, we'll give you 2 options. And of course you also need to start with 2. So if you start with 2, what you're gonna get is 4 is 2. So we have, this is only 1. Right? This will be 1. So start with 4 is 2, from 2 is 1, so added together is 3. So this thing added together is 3. So we start with 2, we get 3. Right? And the thing is, if we start from 4, we'll get 3 as well, because it's just about the pattern. Yeah, I start on 2, and the remaining gave me 3. And then we also can start from 4. The remaining will always also give me 3. Right? The remaining will also give me 3. So those 3 uniques, we can each one I feel like I need more time, and then I'm not really in a good shape at the moment. I think I'll call it. I feel this might work, but a little bit finicky. Right? A bit finicky. Like we analyzed this, and then basically for each one, 2 can occur because this is this is 3 digits. Right, this is 3 digits, so 2 can occur at 4 different positions. Now, when it goes 4 different positions, that's where it gets really bad. Because I can have like a 414 here. So if I put 2 here, then we might get a 414 here. Yep, there's still a chance for duplicate. So we have to fix the first. It just doesn't sit right with me. All right, I'm gonna end it today. So I'll give it some more thoughts, and I'll try it again tomorrow. But if not, I think I'm gonna go look at the hints. Yeah, I just feel it's very complicated, and there should be a way to make it simpler. All right, that will be it. See you guys tomorrow.